Just weeks ago, scientists reported creating a fusion reaction where it produced more energy than it took to start the reaction. How'd they do it?
Great question. They spent a lot of money, they spent a lot of years, and they got really smart people working on the problem.
Well, maybe we can flip this a little bit and talk a little bit about what is the potential,
Yeah.
right? Obviously, we know the challenges we're having currently with fossil fuels, but what is the potential of this type of energy? And why should all of these students here be excited about it?
Right, so if this gets to the point of being, going from experiments to actual working reactors, then it's real. When we talk, this is what stars do, right? Energy is the currency of the universe. But you look at a star, they pump out copious amounts of energy for billions of years. How are they doing it? Fusion. So if we can do the same thing here on Earth, we have the same potential. Now, there's still some competition from fission reactors. They're getting better too. They're getting less waste with new technologies. But this one promises to not have the problems of nuclear waste. And also it's important to recognize that there's different approaches to fusion. So one can lead to a better method. And so that becomes even cleaner and even more energy efficient. And there's even a possibility of one type of reactor that could give you like energy out with virtually no energy in.
Wow.
Yeah.
And the byproducts?
So the byproducts, it really depends, right? So if you look at the two main types, you have inertial confinement where you hit a fuel pellet with lasers, and there's also magnetic confinement, okay? So the problem with both of these reactors is either the fuel waste is radioactive or they're shooting out neutrons, right? So you don't want neutrons slamming into your DNA. Let's put it that way, right? Neutrons are sneaky because they don't have any electric charge. So they can just go wherever they want and not get repelled by the electric charges of nuclei or the electron clouds that surround them. And that can lead to, in your DNA, for example, it hits one type of atom, changes it, because what happens is once that neutron is in a nucleus, it'll decay and become a proton. So now you've changed from one type of atom to a new type of atom that's radioactive. So that's not good.
Is this like Incredible Hulk?
Well, it depends. Some do put out gamma rays, right? But this one, with this type of reactor, like for example, the magnetic confinement ones, they use tritium, which is radioactive. But on all of Earth, there may be only like 20 kilograms of the stuff, right? And so, the ones that use, people you hear about like helium-3, it's not radioactive. Yeah, it's not radioactive, but after the process, the fusion process, it has radioactive byproducts. And the other thing is that there's a type of helium nucleus called deuterium that's used. And so, you react deuterium with tritium or deuterium with helium-3, but there's also deuterium-deuterium reactions that occur, right? And those do produce a lot of neutrons. So you can run into issues. So it's not like perfect yet, but you can screen these things. If you have, say, a meter of concrete, then you can stop those neutrons from escaping, and now you have a much better, cleaner energy source.
But that does bring up the safety concerns, right?
It does.
If something were to happen and those neutrons were to escape, then you have...
Yeah, and so with internal confinement fusion, you have a cleaner system. The other problem is that the magnetic confinement one, sometimes the magnetic field just completely breaks down and dumps all of its energy in a process called quenching. And these things weigh tens of thousands of tons, right? So, all kind of badness is gonna happen if that thing blows up, right? So, there's various approaches. Like there's the standard magnetic confinement machine is called a tokamak. But there's another type called a stellarator, which is gonna come a generation later. The tokamak is simpler, but bigger, heavier, and not quite as efficient. But the tokamak is sort of like a stepping stone to working stellarators, which weigh like much less and are much more efficient.
Outstanding. So the aspect, the potential of clean energy is indeed real.
It is 100% real. That's right. Stars are doing it. So we're humans. We're stars.
Some of us.
They're stars. Yes, our wonderful students.
You get the idea. I've actually had an opportunity to go visit this facility
Yep.
in California
Yeah.
when I was in my previous job. And you get the idea that when people say it's an experiment, you got these professors and they're in a little laboratory with a small, some test tubes and some experiments, and they're making the energy, they put a little bit of energy and they get a little bit of energy out. That's not what this is.
No.
The facility was easily as large as that whole building. And it was a huge reactor and it had a huge control room that looked like you were at Mission Central, right?
Yeah.
And where the actual, every single aspect of that reaction was monitored. Some say the amount of energy produced was somewhere in the neighborhood of about a stick of dynamite.
Yeah.
Is that accurate?
I don't know the actual number, but here's the thing to keep in mind as far as this experimental thing goes, right? So, there's criticisms about this. People say, oh, this isn't generating energy. Keep this in mind. That facility is a multi-purpose facility. They don't just try to do fusion, they also simulate stars. And so the point is, like I said, my other example is if the internal combustion doesn't work, there's no point making the lasers more efficient. This is not a dedicated facility for that purpose. So what they've done is a major leaps forward, and now that you've shown that the internal combustion of your car can actually work and be engineered to work, even though we know it's theoretically possible, engineering it is a different challenge. Now you can go and have a dedicated facility that goes from, inefficient lasers, inefficient experimental process to an efficient process, and then you get to that point where you're getting that clean, abundant energy.
So in essence, the power of the sun can be harnessed.
Absolutely. The power, you know what I call it, because nuclear has become a bad word? Natural mass energy, right? Because, if you look at the nuclear constituents, protons and neutrons, okay? Now, you've heard, a proton is made of 2 up quarks and a down quark. If you add up the masses of the 2 up quarks and the down quark, it's only 1% the mass of the proton. What's the other 99%? That's energy and the gluons, the field that binds them together. So what we're really doing is tapping into that concentrated energy inside the nucleus. So suppose the good doctor and I, President Washington and I, are protons. If you weigh both of us, right, together we may weigh 400 pounds. But suppose now you fuse us, make us Siamese twins. We won't weigh 400 pounds once we're combined. We'll weigh only, say, 360. Where did that other 10% go? That's that energy that was freed, right? Yeah. So that's the power of the sun. That's the power of a fusion weapon that we use. But instead of having an uncontrolled reaction, we now have controlled reactions that we can control ourselves and use it to our own advantage.
Does this mean the end of fossil fuels?
A lot of people will say yes, I say no. And here's why. If you think about it, I give you a gallon of liquid, and that thing can move 2 tons, 20, 30 miles really fast, okay? So fossil fuels they have an energy density, and they're incredibly portable, all right? So the question is, can batteries get to the point where they can replace fossil fuels and having a similar energy density and be just as portable, right? Batteries tend to be incredibly heavy. And so, there's also, what the latest battery technology I learned about that I didn't know existed? You guys heard of gravity batteries? This is nuts, right? So suppose I have something like a wind farm or solar panels. And so in the daytime, I may produce more energy than I need. So what you do is you have some deep shaft or even maybe a house, and you take that energy and you lift the weight with it. All right? And so that energy that you produce now goes into gravitational potential energy. Then at night, when you need the energy, you just let the thing fall and turn the turbine. Isn't that brilliant? Clean, infinite.
Right.
You have sustainable energy there, and you have sustainable energy there, right? So, humans are really clever, and all these things we're doing, it may not be realized in the lifetimes of you and me who are in our early 20s, but for our grandchildren, right, that very well could be the world they live in.
Well, the reality is that many of the individuals in this room will be an integral part of those solutions. And that's why we're bringing this to you today. The whole idea is for us to begin to start having really in-depth discussions about many of these grand challenge topics so that we better position you all to solve them. Man, I wish I had something like this when I was a student.
But somebody did it, right? Somebody you went somewhere and you saw something or you heard something that lit a fire in you and you're like, I want to do that, right? I didn't see myself as a PhD physicist the day I showed up in college, right? That, to me, that was like becoming president. Sure, it's possible, but highly unlikely. And you know what happened? I went to see the astronaut Fred Gregory give a talk, and he talked about how our nation needs you. Humanity needs you. You're the one. You're unique. You're positioned to do this. And I was like, you know what? I'm going to take up that challenge. And, since then, it's just been a joy to be able to be at the forefront of the new technologies and the new breakthroughs in the areas in which I work, right? But of course now, once you discover something, it all depends on personality. Like, I don't celebrate for very long. I celebrate for like a second, right? Then I'm like, dang, now I have nothing. I got to find something new to work on. And now people are expecting even more of me, right? But it's this curiosity, this passion, and that's what, like, if you think going way back in history, right? What drove humans out of Africa to spread across the world? What drove them to create technologies like the bow and arrow to domesticate animals? We've been doing this for thousands of years, tens of thousands, hundreds of thousands, and today we're just doing it at a different level. It's the same process.
Well, then I will extend this challenge. We need you. We need all of you to take up the mantle and to embrace these challenges and to go forth and do great things with them. That is a big part of our future, our shared future. The reality of the situation is for people like he and I, in our 20s, our time to solve these problems is limited. But many of you have an additional 30, 40 years to deal with these challenges, and this is your head start. So jump on it.
Absolutely. And the thing I want to say is, sometimes you step into a laboratory and you talk to the leader. So as an example, there's a Nobel Prize winner. I stepped into his laboratory, Doug Osheroff, and he says to me, Hakeem, I want you to make me a third sound resonance detector for superfluids. I never showed up again, right? You step into a lab, in astrophysics, where I work, right? Someone will say, hey, here's the measurement we want to make, but the technology to do that does not yet exist. So we first have to invent the technology, then go do it. So what does that mean? We do what appears to be impossible, but don't be intimidated by it, because it's just like everything else. It's done a step at a time, and know that you can do it, and know that, that hard work, it actually does pay off in the end. But what our superpower is working together. Everybody has something to contribute, right? What he will see will be invisible to me. What I will see may be invisible to you, right? And so together we can do anything, literally.
Well, this is fantastic. Any parting words for the students?
I just gave them. Come on, join us. Let's do this. You guys are already proving yourselves to be brilliant scholars, right? So, you're baby scholars. I know that's hard to swallow now. You're like, wait a minute, I'm grown. I thought the same thing when I was 19, all right? You're not really grown till you're 50, a year older than I am. Because I'm still, I still have that curiosity and that glee that I had the day I walked in. And other people may look at me and say, oh, you're so experienced. But, when you're working on a new problem every day, you're not experienced. It's always new. And that's what's exciting to me.
So, given the seriousness and novelty of the fusion experiment, how do you see this expanding with multiple future student opportunities, and how can students better get acquainted and sort of involved in this process?
Yeah, so this opportunity is different from many other, early big technologies, in the sense that there's a lot of private companies that are doing it, right? And there's a lot of venture capital money that are going into it. And we need always, if you showed up at my lab and you said, oh, Dr. O, I love what you do, I want to work with you, right? I'd be happy to take you on. Because if you think about it like this, the crisis that we have in STEM, we don't call it a crisis, but we've been pushing science, technology, engineering, and math hard for 25 years. So what percentage of college students graduate with STEM degrees today? It's only 18%, right? And what percentage of those do you think are in physics? Super tiny, right? We need you. So the Department of Energy has summer research programs, for example, SULI, summer undergraduate laboratory internships. So apply for all of these summer internship opportunities, and if you happen to be based near a laboratory, you can actually get, school year positions at them. So many of us who are scientists today, that's how we got into the field. We started off in these internships and, we found one that we love. So I encourage you to try different, my first internships were in physical chemistry, but yet here I am an astrophysicist, right? It's all about the process of doing fundamental research. It doesn't really matter what field you're in, the type of thinking that it requires, right? And that, that being comfortable with the uncomfortable, because it's not like we know what we're doing. It's new, right? And so there's a way that you have to be comfortable making progress when you have no idea where you're going.
So you mentioned when you were talking about gravitational batteries that they tend to be pretty large scale. Do you know if there's any potential for small scale versions of gravitational batteries? Because I've only seen the giant ones that are field sized.
I just got back from Nairobi, Kenya, and there I heard that people are doing it with just an individual home. Right? You build a home on a platform. And as the home or the region generates this excess energy, you essentially lift the home. I don't know if that means that you step out, what was that movie? Up or something like that? You step out of your, right? I don't know how that part's gonna work, how you get back to ground level. But it all depends. The more mass you lift, you don't have to lift it as much to have the same amount of gravitational potential energy there, right? So you can imagine instead of lifting a single home, you lift many, but people are clever. They're gonna figure that out. It's not my field specifically. So when it comes to stuff like this, the devil is always in the details. But what I've recently seen is that there's all these abandoned mine shafts around the world. And the person that did the calculation said that, we have more than enough to convert them all to gravitational batteries to take care of worldwide supply of electricity.
Well, that's the interesting part of this, is that if you're creative, right, there are opportunities that are not obvious.
Right.
Right? I mean, it took not a lot of brain power to come up with the idea of using abandoned mine shafts, right? And you think about it, when you hear it, it's like, yeah.
Why not think of that?
It's so obvious, right? And sometimes the answer, the obvious answer, is looking at us right in the face. And so many of the challenges you'll hear about, you seem like the solutions are so complex and so far out. Oftentimes, the best solutions are the simplest ones, and they may be staring us right in the face.
So you talked a lot about the projects that you're working on, especially going to space and nuclear fusion. That seems like a lot of work. So my genuine question is, what is your day-to-day like? Is it like what we see in the movies where you have thousands of papers lined up? Are you pulling all-nighters? Are you constantly just in dire stress? I just would like to know.
That's what my life was like, right? It's no longer like that because
he's here.
And I learned to delegate, right? And the beauty of youth. Like I was Mr. All-Nighter. And then you get to a certain age, you're like, yeah, I'm gonna pull an all-nighter. And next thing you know, you're waking up in the morning. It's like, oh, I can't do that like I used to do that. But you can. And so if you look at the way research groups work, it is oftentimes, the youth are the ones that are doing the heavy lifting. And there's a great example of that. The Nobel Prize for discovering dark energy from the East Coast side, not Saul Perlman on the West Coast side. I can't remember the guy's name right now, but their research group had a policy that most research groups don't have, and that is whoever does the work gets the credit. And so it was a young cat in the group, not the leader, who did the work on his honeymoon that led to the data analysis that led to the Nobel Prize. And the leader of the group was like, no, you did it, it's yours. Made him the first author and he won the Nobel Prize. Yeah, but we do work together in teams, we do delegate, but we do have those really intense times, right? And you know, it's like when you gotta get the job done, you know, the thing I love about being a scientist is it's not be here from this hour to this hour. It is get the job done. And either you do or you don't. That's it. Yeah, and you know, the other thing about it is if you look at a person that is successful in a lot of things, what people miss, right? What leads you to being LeBron James, right? Is not just that you are physically gifted, is that you are obsessed, is that you are passionate, that you are motivated, right, internally. And so you do that hard stuff, but it doesn't feel that hard to you, right? It's just that I must get this done. I must make this happen. And then you do, and you're like, ooh, I'm really surprised. Because it does seem impossible going in quite often, yeah.
Well, this has been outstanding. Well, thank you. And thank you all for attending the first episode of Mason, Our Future Transformed.